how this increase in our computational capacity has just caused an explosion in the manuals. And are we on? Okay. And a need for greater and greater engineering oversight and knowledge, whereas at the same time, more and more companies are just figuring they can just go to market with a product that doesn't have any engineering. I mean, I'm going to tell you one a little bit later about a company where they have almost no technical expertise and how that got them into trouble. And there's lots of other engineers who look at things, but when people look at things, they're not doing the full thought on things, okay? They're not going through and explaining everything. Okay, no one has any questions? Then let me talk a little bit about design of aluminum, because that's something that you should be interested in. You know, and in my career, I've seen the Navy come full circle on this. Back in the 70s, they built ships. Anybody on a ship that was built in the 70s? Okay, yes. What type? A surface ship?
Submarine.
Submarine. Well, that doesn't count. They don't have a lot of aluminum superstructures on submarines. You were in a sub too? Okay, surface ships that were built in the 70s had aluminum superstructure. No one's been on a ship with an aluminum superstructure, surface ship? Okay. Even the aircraft carriers had aluminum superstructures, didn't they? Okay. Oh, you don't know? Okay. Because they're all painted gray, right? Who knows what they're... You gotta tell from the corrosion. Aluminum corrosion is white and steel is rusty colored. Anyway, but during the Falkland Islands War, the British cruiser Sheffield got hit with an Exocet missile, started an aluminum fire, and wiped out the whole ship. Earlier, there was the Belknap disaster where the Kennedy was out on maneuvers and doing some things, and the destroyer Belknap collided with the Kennedy and didn't do that much damage, except some jet fuel came down on top of the Belknap, caught its aluminum superstructure on fire, and wiped out the Belknap. Okay, so, and I told you the story that the joke at the time was a gallon of jet fuel would wipe out any capital ship in the fleet if they had aluminum superstructures. So in the early to mid 80s, David Taylor, this is Annapolis, which some of you pointed out is this park across from the Naval Academy now, but they actually used to have some real work going on there.
The buildings are still there. I think they're just empty.
Oh, there's some very nice buildings there. I remember when Captain Graham, it was Corky Graham, I don't know if he ever made Admiral, but anyway, he had been a student in 13A, and he rose to the rank of captain, and when he became commander of David Taylor, he took over, he kicked someone out because there's beautiful antebellum type home over there, okay, on the grounds. And he was single, but anyway, he kicked out some other captain or whatever because he wanted to live in this nice antebellum home anyway. And I can remember working there during the summers, and there was one building, I worked in what was the welding and inspection group building, and most of the metallurgists work down in the corrosion group. And if you ever study corrosion, you'll find a lot of data comes from corrosion in Severn River water. Well, that's where the Severn River water test was done, is right there across from the Naval Academy at David Taylor. And so a lot of the data was Navy data. But I can remember there was a big building kind of between the cafeteria and where we were, and if I tried to walk down through there, I had to be careful if I walked through that building, because it was okay to walk on the bottom floor because it was just sort of some old machines and stuff, but if you tried to get it in the upper floor, it was a problem because this is where they did all the sonar research, and it was sort of super classified. But anyway, it never looked like there was any security, but I was told once that an alarm went off in that building, and within 2 minutes there was a Marine behind every tree with a rifle pointed at the building. They just come out of the woodwork, I guess. I guess they live in the trees like the squirrels or something. Anyway, in any case, So the Navy was, in the early 80s, was trying to do waffle membrane construction of the superstructures. They've got to be light, and essentially they were using high-strength sheet metal steel, and they were making something that looked like a cross-section of corrugated cardboard, okay, in steel to replace the lightweight aluminum structures. It's a serious problem for ships in general. Does anyone know, as people get older, they gain weight, and I'm a pretty good example of that, but does anyone know what an aircraft carrier gains per year in weight? 250 tons a year. If you plot the Nimitz class carriers from, the early 60s all the way up through the 2000 or so, they gain 250 tons a year. And most of it's up top, right? So, yeah.
What you're talking about is one carrier to new carrier.
Yeah.
That character is typically gaining weight due to rust or something.
No, not due to rust.
Okay.
New equipment that was never existed before, okay? I mean, new radomes and whatever, but new equipment, and even an existing sub will get heavier and heavier with time. It's just like, haven't you ever lived in a house and you have more stuff when you move than when you started with, okay? Well, carriers are sort of the same way, okay? And part of it is they keep adding more things to them. It's a problem for the Army soldier, okay? Or actually, you can see it if you look at a policeman. Look at what a policeman wears on his belt now. You wonder that he can even walk with, the belt is just this thing to carry all this other stuff. And there's not much room to carry anything else. Same thing for an Army soldier. They're predicting that they'll be carrying packs of 150 pounds, and half of that's going to be batteries for all the electronic gear they have. So things get more and more complex with time. So they were trying to get rid of the aluminum so they wouldn't have the aluminum fires, and they were trying to keep the weight down. And then the next thing I know, by early 2000, after the World Trade Center fires and stuff, they basically decided that and peace had broken out with the former Soviet Union, and you didn't need a Seawolf submarine anymore. You needed littoral craft, okay? I never heard the word littoral before. Most people hadn't. And so now they're high-speed aluminum craft, and you built them, right? But the problem with aluminum is it's a lot more difficult to weld than steel. It doesn't corrode as much. It can catch fire, but the Navy's sort of given up worrying about whether it catches fire or not. If it catches fire, it does. Anyway, if you look at we talked about the old aluminum structural welding code before 2000, and it was thicker than the one today, but it had a design section. But by 2003, it actually got thinner because they essentially included the Aluminum Association's Aluminum Design Manual, which has a fair amount of thickness to it. But in fact, if you look at allowable design stresses for aluminum, you'll find, this is for all kinds of structures, they have details and fatigue design details for things in greater concentration than you'll find in the steel literature. Does anybody know anything about the properties of aluminum that make fatigue a greater problem for aluminum than for steel? No one? Okay, well, you will learn at some point that if you look at the stress versus number of cycles, for steel you get a fatigue curve that comes down and looks like this. And so this is high stress and low numbers of cycles. This is log cycles. So somewhere around 1 million cycles or 10 million cycles, the thing levels off for steel and has essentially infinite life, which they usually draw as an arrow going out. For aluminum, you'll be considerably weaker, but the curve just keeps going down. And people have gone out to 10 to the 8th or 10 to the 9th cycles, Takes a long time to get 10 to the 9th cycles. But in any case, it just keeps on decreasing. For steel, the fatigue limit is somewhere between 0.45 and 0.5 of the yield stress. For aluminum, there is no fatigue limit. If you fatigue the aluminum long enough, the acceptable stress level will keep going down. This was a big problem for introducing aluminum wheels in trucks, okay? They had aluminum wheels in cars back in the 60s and 70s, but it wasn't until the 90s really that aluminum wheels in trucks took off, and that was when they got sophisticated enough computers to do a good enough stress design to know exactly what the stress was, and they were using supercomputers to design truck wheels, okay, out of aluminum. But aluminum has this problem of having no fatigue limit below which the material will not fail in fatigue. Where'd my pointer go? Okay. So anyway, the aluminum design manual has all kinds of connections, whether they're bolted or welded, and different categories, A through F if I remember. And the E categories are not quite as bad as F, but things where you wrap a weld around and you have lots of residual stresses and stuff, you end up getting fatigue cracks fairly easily. There's some famous bridge failures that occurred because of that type of doubler plate design where they wrapped around. There's one in Australia that was a big surprise about 50, 60 years ago to the designers of steel. And a lot of those details that I just showed you come exactly out of the steel construction manual in terms of weld type details, but they apply to aluminum, but they apply in a lot more complex ways. Aluminum doesn't have the strength of steel. It's got about 1/3 the strength of steel. I mean, you can get 60, 70 KSI yield aluminum alloys, which are heat-treated aerospace alloys that they're not very weldable. But most of the weldable aluminum alloys that can develop full strength in the weld, there's a host of alloys with a number of different filler metals. You can't just use any old filler metal with aluminum. If you use the wrong filler metal with the wrong alloy, then it's going to crack, and you can't prevent it. There are some aluminum alloys just cannot be welded without cracking. A lot of the 2000 series that they rivet aircraft out of, they rivet them because they can't weld them. If you try to do fusion welding on a 2024 aluminum, you just have cracks in the heat affected zone. Okay? So in fact, what they typically use for welding of ships and things are 5000 series. The problem with those is they've only got 20 or 30 KSI yield strength. Well, that's significantly less than something like an HY100, which is what you build a submarine out of today, which is 100 KSI, right? So it's got 1/4 the strength of a submarine steel. It's got about half the strength of the plate on a surface ship, okay? So aluminum doesn't have the strength, the yield strength, it doesn't have the fatigue strength, and you have to be very careful about what filler metal you use. You can hear about wonderful aluminum alloys with tremendous strength. Anybody have an idea what the highest technology strength for aluminum alloys? You can get aluminum alloys close to 100 KSI yield. What the application is? Baseball bats. Okay? Turns out they slim them down and they slim them down, and they have special alloys used only for baseball bats, and they heat them up and they quench them in ice water in order to maintain fine grain size, and they will get higher strengths than anything used in any aircraft. Okay? But they're very thin. Okay? They're about 20 thousandths thick at some spots. So anyway, sometimes it's sort of interesting to find out where the real technology is in something, but if you actually look at the market size, it makes sense. Some of the most sophisticated stainless steel goes into razor blades, okay, for example. Okay, why? There's a lot of razor blades out there, okay. In any case, so there's this complex table that you don't really have to understand right now, but you should know that if you're welding a particular base metal over here, there are all kinds of weld metals and you can only choose certain combinations, and it's much more restrictive than steel. But rather than that, what I wanted to show you is the structural welding code for steel is actually fairly simple. It basically says that the safety factor for a building is 1.67 and for a bridge it's 2.0. But for aluminum, the safety factor or the design stress level becomes a function of the alloy that you're using. And the strengths that you can use, remember I told you you could have 20 to 30 KSI yield strength. The fatigue strengths for allowable shear are significantly less. You can only use about 1/3 of your yield strength. So you only have one half to 1/4 of the yield strength to begin with compared to steel. But instead of being able to use about 60% of that, which you can in steel, you can only use 1/3 of that. So you're getting down to design stresses in some cases of, well, 1100s, like frying pans. It's relatively pure aluminum or aluminum foil. But you're getting down to design stresses of 5 to 6 to 8 KSI ranges, which is not much stress at all. It's not much more than the yield strength of a good plastic. Okay, so it might be aluminum, but in terms of fatigue strength long term, it's really not much better than plastic. Okay, it's got more toughness than plastic, and it has certain other advantages compared to plastic. It will burn, but it's harder to burn. But anyway, so you end up with a very complex manual, much more complex than any steel construction manual, just because the aluminum metallurgy is much more difficult than the steel metallurgy. Okay, and so we've got a proliferation where we've gone from a manual of 15 years ago where everything you needed to know was in this, to now a manual of nearly that size plus all of this. And you really have to, I could show you the pages with all the stress design calculations and stuff, but you have to be a fairly sophisticated civil engineer or structural engineer to do it. I mean, I go look at the aluminum design manual, and you know, I used to know how to do it in the 1997 code, but you know, I go get an expert now on aluminum design to go through things. It's just a lot messier. And that's part of the explosion of the codes. I've talked about the codes have gotten much more complex. And that means you need more and more specialty. And it's the same in most things, okay? Whether it's medicine or whether it's ship design, things have gotten much more complex. At the same time, I'm finding more and more entrepreneurs, small businesses start up and decide, we don't need all this engineering overhead. We can go market our product and we'll just kind of let our suppliers do our engineering. And so you end up with new products that, some of which are successful, but some of which end up becoming a disaster. And so what I wanted to talk about that there was corrugated stainless steel tubing. Anyone ever heard of corrugated stainless steel tubing? Okay, this is gas tubing. It's fuel gas. Originally it's in yellow because that's the international code for fuel gas tubing. You know, a plumber goes in a building or a firefighter goes into a building and they see yellow tubing, they know that probably carries a flammable gas. Okay, sort of a warning. So it replaced black iron pipe. What happened was in the early 80s, the American Gas Association or the Gas Research Institute, I can't remember which one, they're both located in Ohio if I remember, they decided they wanted to promote more use of gas. Well, you can understand why. And they were also concerned about the fact that most of the steel piping that had been put in in the 1920s and 30s and 40s and 50s was corroding. I mean, they bury the steel pipe in the ground, and particularly in New England, in Arizona it's not so bad because it doesn't rain that often, but in New England it rains a lot, the water's wet, or the ground is wet, and this stuff corrodes. It's about 1/8 of an inch thick in small diameters, but it takes a while to corrode. The U.S. Army did a study of 25,000 underground storage tanks, and they show that the typical corrosion rate, you'll perforate 1/8 of an inch of steel in 5 to 25 years, depending on the soil conditions, part of the country, amount of rainfall, pH of the soil, electrical resistivity of the soil, because the corrosion current's got to be carried through the soil and things like that. But typical time to perforation of a pipe is 5 to 25 years for an underground storage tank. So how come, you know, all through Boston they put in gas piping in the 1930s? I mean, I live in a house built during the Depression, and going down our street, gas piping like this. And well, there wasn't, well, actually there wasn't, actually, what did they use before that? Originally for gas piping, they used wooden logs that were gun drilled out, okay? And they would caulk them up with some oakum and stuff. And then they got to cast iron pipe in the 1880s. But all they used gas for back then was street lights, okay? But it was in the 1920s or so they started using, you know, corrugated or steel piping. But that pipe is running down my street. The water pipe and the gas pipe have been there for 70 years, more than 70 years. Why? Why isn't it full of holes? Well, it is full of holes. I mean, you know, science is science. But it's surrounded by mud, and the mud seals it. So it does have a hole in it. Big deal. It's just leaking a little water, or, you know, some estimates state that like 25% of the water that a utility pumps is lost through leaks in the system into the ground. Okay, so you're watering the trees for free, okay? What God doesn't do, we do, you know? And for water pipe, what's the big deal? For gas pipe, oh, so you leak a little gas into the ground, that's where it came from to begin with, right? What's the problem? So I didn't understand this until about early 80s or something, maybe mid 80s. 7 o'clock one Sunday morning, my neighbor 2 doors down calls me up and he says, "Tom, you've got a leak in your front yard." Tony's been he is a machinist for 60 some years, and he woke up early, and he likes to wander around. He's a very friendly busybody, okay? And I look out, and sure enough, I have this little 4-inch sprinkler in the middle of, you know, between my sidewalk and the driveway and the street. And so I call the town water department. It's Sunday morning, and by 10 o'clock they got their backhoe out, and they're digging up the street to get to the valve to close this off. And as I'm sitting there watching the backhoe in the street in front of my house, and they're digging this pit and they're getting down there, I start smelling gas. And right then, back then it was Boston Gas, the Boston Gas truck pulls up, 10 o'clock Sunday morning. And then I look over, and the guy running the backhoe jumps out of the backhoe, takes some chewing gum out of his mouth, jumps in the pit, and plugs a leak in the pipe, in the gas pipe that was next to the water pipe. And I said, "How'd you guys know?" They said, "Whenever we uncover any pipe around here, we know we're going to find leaks." So they actually automatically call the gas company whenever they start digging, because it's full of leaks, folks. That's the infrastructure. And so another 15 years later or whatever, the gas company has to go through these neighborhoods, older neighborhoods, every 3 years by state law, another standard, okay? And they have to put sniffers in the ground to sniff the amount of natural gas in the ground. because it's leaking. It's saturating the soil. And if you have a really bad leak, the plants die. So you can often tell, you know, if you have a bad a spot of ground where you can't grow any grass, or you have a shrub that keeps on dying or something, it's because you probably have a gas leak there. Okay. So in any case, they come sniffing down the street, and 2 houses, mine and another one, they find too much gas in the soil. So what do? They sleeve the pipe. It's too expensive to dig it up and replace it, and they wouldn't replace it with a new steel pipe anyway. They'll replace it with a plastic pipe. But what they can do is that in the street, if they find a leak in the pipe, they dig up the street, they run a plastic sleeve pipe through here into my house, don't dig up my front yard, and everything's fine. Well, except it's not fine. They have to make a plastic to steel connection on the inside, and a week later we go to listen to some kid's concert at one of our children's concert at the school, and my wife brings the younger ones home early to put them to bed, and she smells gas all throughout the house. I get home half an hour later, there's still gas all throughout the house. She'd called the gas company, it's pouring rain, and they come out, and that little plastic to steel connection is leaking gas. It is one of the strongest gas smells I've ever smelled inside a building. I mean, I don't know that we were at the explosive limit, but we weren't far from it. It could have blown up my house, okay? And everything would have been fine, except they put in a work order to fix it, permanent fix. He just came and put some putty on. It's raining out, middle of the night. So he just put some putty on. He says, I'll put a work order in. He put the work order in, but then Boston Gas lost the work order. And my wife called him up. I told her to call him up after about 3 weeks. And they said, we don't have anything. And they started arguing with her about whether we had putty on our connection in our house, and telling her she didn't know what she was talking about. So I got involved, and I called up the regulatory authorities, another set of people who set standards, right? And I tell you, I was getting calls here at work every 20 minutes from high-ranking officials at Boston Gas. There were like 10 trucks that converged on our house once the state regulators basically told them, go and fix it, okay? They probably got I don't know what happened, but they probably got a nasty letter at least from the state for having lost the fact that they had made a temporary connection and not fixed it, okay? Anyway, so what happened was they had concerns about all this corroding gas piping in the early 80s, and they were looking for solutions. And what's the solution? What's the piping now they put in? Anybody seen the gas piping? It's plastic. And the plastic won't corrode. The plastic has other things, problems, like it's brittle, and so it probably won't last an earthquake, but if we have that bad an earthquake, a lot of other things won't last either. But they decided in Japan, the Japanese had developed corrugated stainless steel tubing for gas, because they do have a lot of earthquakes, and they were worried about fires. And if I had a longer length of this, you'd find it's very flexible, comes in big coils, 3 or 4 feet in diameter. Costs about $5 a foot, okay? So between 1997 and, 1987 and 1997, they have to go out in order to market this. They hire a guy out here in Waltham, Massachusetts, works for Foster Wheeler, and he goes around, he writes a standard, okay, called ANSI LC1, which they basically they incorporate that standard in Canada, because the Canadian authorities, to develop a new standard for gas piping, have less bureaucracy than the United States. But since they get it in Canada, the Canadian standard essentially gets sort of reciprocity as a US standard, and it becomes an ANSI standard, ANSI LC1, and they will now sell it to you. It's all of about 60 pages long. It'll cost you $600. I just bought a copy for $598. Okay. So again, it tells you about the price of these things. But they have this standard. They incorporate the standard on how to install this stuff, because you have to have special fittings. There's about half a dozen manufacturers of this stuff now. By 1997, they start marketing it because they've gotten approval from various state agencies to allow this into the plumbing code. Before that, the code wouldn't allow you to use an innovative material, right? So there's how codes stifle innovation. Here's this wonderful new material the Japanese have been using, and we couldn't use it until they spent 10 years. The Gas Research Institute or American Gas Association, whichever one, spends 10 years getting enough states to approve it that certain companies will start manufacturing it. In fact, we've been using this stuff for 50 years. You can go to Home Depot and look up how to install a gas stove or a gas dryer, and they will sell you links from 3 feet to 6 feet long of this corrugated connectors made by 2 other people, and they've been making it for 50 years so that you can pull your appliance out from the wall. You don't have it hard piped to the wall. I mean, my furnace at my home is a gas furnace, and it's hard piped with black iron pipe. I can't pull it out from the wall. But your stove, you want to be able to get behind your stove to clean all those little rat droppings and stuff, or whatever. Or you want to pull out your dryer, okay, to clean all the lint from behind there. And so we had been using this stuff, but we hadn't been using it in 100 to 200 foot lengths in homes. And why is it such a wonderful product? It's such a wonderful product because it's light, it's flexible. Instead of having to thread 15 or 20 pieces to go from the gas meter to your stove and then have one short little piece of this stuff, you have one piece and you can thread it through the walls without cutting down the walls, and it's just easy to install. And so they get this stuff, maybe 70 cents a foot, this stuff $5 a foot. It has less value of material in it than this one almost, even though it's stainless steel. But they get a tremendous markup. And so between 97 and today, 15 years, there's 1 billion feet of this stuff out there in American homes. Anyone have a relative, most of you are probably too young to have big homes with fireplaces on the second floor in the master bedroom, or a gas fireplace in the den. Any of you have homes like that? Or do your parents?
My mother has a gas fireplace here.
Yeah, okay. And they now have gas piped out to your barbecue grill in some places rather than using a propane tank. Yeah, right? I'm getting some nods. Why? This is the miracle product that makes it possible. Instead of, we used to have maybe 50 feet of black iron pipe in a home, we now may have 200 feet of this stuff, and we have gas appliances all over the place. Fireplaces in the den, in the master bedroom, barbecue grills, everything's becoming gas, and so it served the function that the Gas Association wanted, to promote the use of gas. Until about 1990, started selling in 1997. By 1998, they started noticing they had a few more fires than they were used to that were not explained. So this is an innovative product. But no one ever thought about what would be the effect of lightning on this product, okay? And the effect of lightning is that if lightning hits it, it will blow a hole in it, okay? Now this was not done by lightning, this was done by an electrical circuit. The smaller holes by a 20 amp circuit, the bigger holes by a 40 amp circuit. You get an arc to this stuff, and 1/10 of a coulomb, they actually characterize the strength of a lightning strike in coulombs. A coulomb is an ampere is a coulomb per second, right? So a coulomb is 1.6 times 10 to the 19th electrons or something like that, or is it 6? I can't remember. It's 6 times 10 to the 19th or 1.6. But anyway, so a typical lightning strike is 3 to 5 coulombs of charge. They can go up to 400 coulombs in a really big lightning, but that's pretty rare. They easily can go up to 80 coulombs in a big strike. This stuff can sustain 1/10 of a coulomb without perforation. Okay, So what do you think the odds are of getting a hole in this if you get hit by lightning in your house? Pretty good, huh? Well, so the industry acknowledges that by 2001 they knew about this because they started doing research at the old General Electric Lightning Research Center in Pittsfield, Massachusetts. They used to build transformers, electrical distribution transformers for General Electric, and they had to deal with simulated lightning strikes because it can get really exciting if lightning hits a distribution transformer and all the power goes out and things like that. So they have to protect these things from lightning. And I gave you the Ben Franklin article about lightning protection systems and stuff. Well, this stuff they certainly learned by 2001. There's some evidence they learned they started learning within the first couple of years. If you look at the National Fire Protection Association data, you see in 1998 a big jump in the number of fires due to lightning from fuel gas in homes. So there's about somewhere between 500,000 and 1 million out of the 65 million homes in the United States have this product in them. Okay? If it's in your home or a relative's home, get a lightning protection system. It only costs you $4,000 or $5,000, and think of all the money you saved on the installation of your gas piping. Okay? So you can take the money you saved and now protect your home that it won't burn down in case a lightning storm comes by. Anyway, so there's 1 billion feet of this stuff. So they realized they had a problem. By 2003, they decided that they could, a number of patents came out by different people. They decided that they could improve things by making a conductive jacket. And so they basically, I think all they did was add carbon black to the plastic, and now it looks like a tire with carbon black in it, an automobile tire. But one of the products made by Gas-Tight actually has 2 layers of plastic with a layer of corrugated or not, perforated aluminum in between, and the Gas-Tight product will sustain a lightning strike of 80 coulombs, 800 times safer because of that second layer of aluminum in terms of a lightning strike. Okay? There's another product made by a competitor, and they came out with just the conductive plastic, and it will sustain about 6 coulombs. Okay, so 6 coulombs. If this is your median, and they're at 6 coulombs, I'm not sure I'd want that in my house. I think I'd rather have this in my house. But if I really want to be safe, I would have black iron pipe, because to my knowledge, no one has ever heard of lightning. Theoretically, it's possible, but no one has ever heard of black iron pipe being perforated by lightning. Okay? Why? Well, you can go through the heat transfer. If you go through in the welding section, I'll talk about the distance that heat travels in time is going to be proportional to the square root of the thermal diffusivity times time. This is a proportionality, and that's alpha thermal diffusivity. The thermal diffusivity of steel, if it's 1/10 of a centimeter squared per second, okay, and the distance the heat travels, if we're talking about a circuit breaker which might close, how fast will a circuit breaker close? Anybody have an idea? 1/100th of a second. Okay, half of a 60 cycle. Okay, so it's 10 to the minus 2 seconds. So I have the square root of 10 to the minus 3, which is what? 10 to the minus 3 is 0.03. X is equal to 0.03 centimeters, which is 0.3 millimeters, which is 12 thousandths of an inch or so. The CSST is 10 thousandths of an inch, so it will blow through CSST in the typical time that you might have, but it won't blow through black iron pipe, which is 1/8 of an inch, which is 10 times thicker. Okay? Now, in fact, I kind of simplified some of the heat flow here. I didn't solve the partial differential equation. time-dependent solution. And the real solution is about 0.3, not 0.12 inches. And it just so happens the guy at University of Florida caught some triggered lightning. You can stick an antenna up there in the air in a lightning storm, and you can try to attract the lightning, a real lightning bolt. It's called attracted lightning, okay? And he got a 7 coulomb strike, hit a piece of stainless steel. He was doing this for the Department of Energy for the nuclear waste isolation materials in Nevada. They wanted to make sure that one of these like 3-inch thick stainless steel casks wouldn't be perforated by a piece of lightning. Oh gee, I'm sure they probably spent $10 million proving this, where a simple calculation would tell you that there's no way that you could do it, okay? But, they have to prove to everyone, right? Because no one trusts them. In any case, the simple heat flow says you'll perforate this stuff. It's just too thin if it gets hit by any kind of reasonable lightning strike, whereas stainless steel black iron pipe is thick enough that it won't be. And there's actually codes for the thickness of lightning terminals, lightning rods. And it tells you that a lightning rod should have about the cross-sectional area of a piece of black iron pipe. And it will tell you this stuff in stainless steel is 5 times too thin in cross-section to carry the current to ground. So what happened? Okay, they started out with this code in the 90s. They got it approved by different state agencies because to install gas piping has the force of law. I'm trying to tie this back to codes and standards, right? So they tie it back to all this, and they find out about this. In the meantime, they don't really tell anybody about this problem. Okay, I mean, some people know about it, but they're sort of trying to hide this. Now, why are they trying to hide this? Well, you can't hide it completely, because when people's homes start burning down, they sort of get upset, and insurance companies come in and they start looking at things, and they get a little concerned when they start seeing these holes, and people see jets, 3-foot jets of fire shooting out of their gas piping, burning down their house. And any case, so they start having some lawsuits, and what do? They blame it on the plumber who installed it, right? Blame it on someone else, right? It's not the fact that you engineered it wrong or didn't even consider lightning to begin with, which they've admitted. We tested for earthquake resistance. We tested for these other things. No, we didn't think about lightning. Okay, you didn't think about it. Well, that's the problem with a new product. You can't think of every new thing necessarily. But when you kind of get slapped in the face with it, you don't try to deep six it. Okay? Well, up through about 2007, they were laying this off on the plumbers, saying you didn't ground it. And to give you some idea of the grounding, let's say I got a fireplace, and here are my logs in here, and I got my nice flame in here, and this is a gas fireplace, and I got my tubing coming out of here, and let's say I also have some electricity coming in here, and it's grounded because they have a little electrical igniter, so you just hit a button to turn on your fireplace, right? So it's got electricity in here, it's got gas in here, and you might ground it to this, and of course this is electrically connected to that, but no, they told you to ground it to their ground, and their ground means you have to ground it to one of their fittings, okay? And they'll sell you these fittings. Now remember, there's 1 billion feet, and they're selling it at an average of $5 a foot over the last 15 years. So this is a $5 billion business over the last 15 years, plus the fittings, okay? It's a fairly substantial business, and they don't really want to lose it, because some of these guys, they've got a lot of education. One of them graduated from high school. Another one has 2 years of auto mechanic school, and he's the top engineering authority in this company. He has more technical education than the whole rest of the company combined, because he had 2 years of auto mechanic school, okay? And they're designing gas piping for the country. But they're making $1 million a year, okay? with their high school diplomas and things by selling this stuff, because it saves plumbers. A plumber can plumb a house in 1 day with this piping, where it would take 3 days if he had to thread the black iron pipe and screw it together and everything else. Tremendous savings in installation costs. Anyway, they say if you don't ground it electrically here as opposed to over here, it's no good. You didn't follow our standard. Well, do you think the electrons care? How do they get to ground? You know, whether it's through here or through here? No, I don't think the electrons care. Okay, but they would blame it on the plumbers, and the plumbers' insurance companies would pay off. Okay, but then if you start thinking about this grounding, the grounding doesn't occur. This is not DC electricity. How many electrical engineers do we have? You're an electrical engineer. So what's the difference between resistance and impedance? You remember? Resistance is what we talk about, the resistance of the material to electrical flow in DC, right? And impedance is the resistance to electrical flow when we have higher frequency components, right? Yes, and what's the difference? Do you know the difference?
Well, impedance includes storage of energy in fields.
Exactly. In fact, the whole area of complex numbers is used to define AC electricity. You have to go to complex, and have you done complex numbers this summer? Not yet. I bet you get to, okay? You get to go through complex numbers. And so there's what they call in complex numbers, the real component and the imaginary component. The imaginary component is the storage of those fields. And I mentioned to you before that if I have current going through a conductor, that there's a magnetic field, okay, that is around that conductor due to the flow of the current. That's one of Maxwell's equations. It says if I have a current, I will have a magnetic field around that. And so it turns out that if I have two conductors side by side, and one of them has current going through it, there is what we call the inductance. And the inductance is this storage of magnetic field. As I try to increase the current from 0 to some higher value, I have to create the storage of this magnetic field around this thing. And at lightning frequencies, where I have rise times of 40 million amperes, 40 billion amperes per second, okay? I'm sorry, 40 billion amperes, yeah, 40 billion amperes per second, which is 40,000 amperes per microsecond, okay? That's the rise time of a lightning strike, okay? It's fairly fast. And the typical inductance of any conductor is about 1 microhenry. So if I take 40,000 times 1 microhenry, and the AC impedance simplified is the inductance L times di dt. This is the change in current with time. This is the inductance. That's on the order of 1 microhenry. This is 40,000 amperes per microsecond. So this is microhenries, that's microseconds. So you get with 40,000 volts. If I have two conductors in a house parallel to each other, and lightning hits and gets into one of them but not in the other, within 1/100,000th of a second, I will have 40,000 volts between these two conductors. And what happens then? Well, it takes 20 to 30,000 to perforate the plastic, and so you get an arc between these things. Boom! You got a hole, you're off to the races, you got a fire in your house. And one of the things they did is they came up with a better product. So what do they do at that point? What should you do at that point to protect the public? When you know you have a product that's good for 1/10 of a coulomb, you know that lightning strikes can be 3 to 5 coulombs, you've got a better product, that can take however many coulombs, what do? You keep selling the old stuff? You're saying no.
Might even recall it.
You might even want to recall it. You could, or at least warn people that it's in their house so that they could do something like install a lightning protection system at a cost of $3,000 to $5,000, right? But you think the people would be happy? Probably not. In fact, in 2003, there was a class action in Arkansas, okay? And I don't even know what happened. Well, the class action got settled, I know that. But in fact, one county in Texas has outlawed the use of this stuff, okay? So it's no longer legal in that county. But most other places haven't. And what do? Until September 1st of 2011, they kept selling this because it was 8% cheaper than their version of this. They were trying to get a markup for the safe product and still selling the unsafe product. That's really responsible, isn't it? Okay. And their argument is they met all the codes that applied to this, which was ANSI LC1, which just happened to be written by them and ignored lightning altogether. Okay? Do you think this is ANSI LC1 is the only code that would apply to this? I showed you other codes that will call out 20 different codes, right? ANSI LC1, probably I'd have to go back and look at it. It probably calls out some other codes, but it didn't even consider lightning or AC effects of electricity or anything like that. And they learned that, oh, we made a mistake. We should have considered those things. They developed a new product, a better product. I'm not sure if, well, the one I have there, the black stuff, that one may be safe. The stuff that replaced this stuff, different manufacturer, I'm not sure is safe. But even still. But they tried to get an 8% profit off the better product and kept selling this stuff. In fact, they still sell this stuff outside of North America. Okay? Because other people don't know about this problem yet around the rest of the world.
Lightning problem in Japan, where they originally developed this?
Well, the argument is Japan doesn't have as many lightning storms as other places. If you start looking at lightning frequency tables, California has 1/50th the lightning strikes of Florida. Florida's got the most lightning strikes of anywhere in the United States. Okay, the Midwest has lots of big lightning storms. I mean, you know, tornadoes and all this other stuff. We have a fair amount of lightning. We're supposed to get lightning tonight, so go check out your gas piping in your house. But California and Japan, the lightning is has a lower frequency, and you have to now start looking at the building codes and stuff. I put in a gas generator in my house 3 or 4 years ago and had the plumbers come in, and they put in about an 8-foot length of this stuff. It's in my basement. Have I replaced it? No, because I have trees that are twice the size of my house within a few feet of my house, okay? I live in a valley. I don't really live up on top of Belmont Hill with the rich folks. I live in the valley, okay? This is down in my basement. It's right beneath the power line coming in, which is grounded and essentially a lightning protection system for it. So I look at all those things and say the chances of my particular installation getting a perforated hole, plus it's not even I calculated these things are safe if the length is less than 10 feet, which explains why all these other connections we've been using for 50 years are safe. It's the 100-foot lengths. It turns out there's a length that goes into this LDIDT. Okay, I didn't give you the whole formula. But the longer the lengths of piping you have, the greater the voltages that you're going to set up between things. Okay, so this is 40,000 volts. I didn't tell you, it's actually 40,000 volts per meter. Okay, so if I have too many meters of piping, I got real problems. Okay, so in fact, I can show you a book on lightning that claims that you can develop 2.5 million volts. Okay, not just 40,000. Their calculation is the same calculation, but a little more sophisticated. They use 2 microhenries rather than 1. Anyway, you can come up with some pretty huge numbers for the voltages which are going to start the arc that starts the hole. Okay, So what's happened in this? Well, when the National Fire Protection, there are, let me go back to where I was. There are other codes than ANSI LC1. One of their defenses, they say, well, we met all the applicable standards, which is ANSI LC1, which we happened to write, which ignored lightning. But we met it, and so therefore we must be safe. That seems like circular reasoning to me. But it's not the only code. If you're using propane, there's NFPA 58, which is the propane gas code. And if you're using natural gas in a house, there's NFPA 54, which is the fuel gas code, which is the National Fuel Gas Code. It's also an ANSI standard. And both of those two codes are written into the laws in most states. The plumbing authorities in Massachusetts is the State Plumbing Board, okay? Gas fitters and plumbers, right? They have adopted NFPA 54 and NFPA 58 as part of the law. A plumber must install gas piping according to the code. Now, what happened? How did they get, and we can use Massachusetts as an example because I was involved in part of that. In 2003, the company that made this stuff, before they had this stuff, but they had something that looked just like this, just different name on it, came to the State Plumbing Board and said, we want to get authority to start installing this in Massachusetts. This was in 2003, when they already knew about the problems with lightning, okay? They didn't tell the plumbing board about the potential problems with lightning at the time. And frankly, I wasn't asked to evaluate lightning at the time. I was asked to evaluate the problem because some of the plumbers said, well, what if you put this in the wall and someone comes along and drives a nail in the wall and perforates it? Now you're going to have a leak that generates a collection of gas in the wall. And if it reaches an explosive mixture, you can blow up the house. That doesn't seem like a safe product. Whereas the good old black iron pipe, 1/8 of an inch thick steel, not very many people are going to be able to drive a nail through that that's not going to be deflected, right? When it hits it. But this stuff, you hit it right with a nail and bang, it just goes right through it. And it's happened, okay? And they said, oh, we have a solution to that, because they did think about that problem. They had hardened steel plates, which they said, you put these wherever you have the stuff going along the floor and turning up into the wall, you put one of these nail plates in right at the floorboards, okay? So if someone's nailing in the wood stripping on their at the floor, the wall, what do you call that strip? Molding. The molding. If they're putting in the floor molding and they try to nail in the floor molding and they hit the gas pipe, we have a nail plate that you put in front of that. And I thought, well, what if you're hanging a picture? Very good. I thought about that too. And their answer there is, well, there it's just in the area and it can flap in the breeze, so hopefully the nail will just push it aside. Okay? Well, we can all hope. Hope springs eternal. So I ended up writing a letter or an email to the State Plumbing Board because I'm friends with the chairman of the State Plumbing Board. He asked me to look at this problem. And so I looked at their solution of the nail plates, and I said, well, the only way to make it safe is to put a nail plate around the whole thing, which means the only way to make it safe is if you take this flexible tubing and encase it in black iron pipe, right? Because that's putting a nail plate all the way around it, right? Everywhere. And I wrote that as my little letter to the State Plumbing Board. And so it turns out, I learned just a year ago that from this chairman of the State Plumbing Board, that the attorneys for the people who made this that were trying to get approval had come to the State Plumbing Board and threatened to sue them for restraint of trade if they didn't approve their product, okay? And the State Plumbing Board, armed with my letter said, this was back in 2003, and I didn't know this at the time, said, well, you either accept our restrictions on how you install this stuff, or else we're going to release Professor Eager's letter to the public. Okay? And they accepted all the restrictions of the state of Massachusetts. As a result, the state of Massachusetts has some of the most restrictive requirements for installation of this stuff as anywhere in the country. So this is the little extortion goes on between the company and the state plumbing board. Well, there are national codes like NFPA 54 and 58. Well, NFPA 54 governs the installation. Well, actually, how did they say it? No. Anyway, NFPA 54 committee, I think, has basically said they are not responsible for the part of the code. There are other NFPA codes that apply to this, but the code committee, the NFPA, National Fire Protection Association, had given approval to this, but by 2007 or 2008, there were enough questions about this that they basically went back to the companies and said, well, we gave you a 10-year approval, which expires in 2014. You have to prove to us by 2014 that your product is safe. Why didn't they just remove the approval?
Head off a lawsuit?
Yeah, they were going to get sued, just like the companies had threatened to sue the state plumbing board if you don't approve our product. Here, the NFPA had approved the product for 10 years with a potential renewal in 2014. And I have a copy of the letter from the NFPA committee in 2007 or 2008, whenever it was, saying, we require you to prove that the product is safe, or you will not get approved in 2014. So they don't want to get sued for restraint of trade, okay? But they can decide whether they're going to renew it in 2014. So that's kind of where that is. The companies went to trial once, they lost. The product was found defective. They're on appeal. They've removed the yellow stuff from the North American market and are only selling the improved stuff. But this is just another side to this whole codes and standards. Here was an innovative product, okay, that had significant advantages and cost savings. But soon after it was introduced, they learned that it had certain problems. And here you have the tension between the company who wants to continue to make profit, because, you know, who wants to, you know, comparing $1 million salary with 2 years of what you can get as 2 years at auto mechanic school, you know, there's just really no comparison. And so they want to keep it going. They maintained it safe in the very beginning, and it was just because the plumbers forgot to ground it. But then we had homes where it was clearly grounded, and they still had the problem, okay? Now, I pointed out that single point grounding, 1 point in your house to ground it, is not good enough. The lightning can only see, in the time of the lightning flash, can only see a distance of about 10 feet in any direction. So you basically would have to ground it every 10 feet. But even by their own code, you can't ground it by clamping to this. You have to ground it at one of the fittings, and there could be 50 feet between the fittings. So how do you ground it every 10 feet? You can't, okay? So what's happened in the last 5 months is well, actually, I should say the last year, their lightning expert basically said, you should have a lightning protection system. This is what Ben Franklin said in 1752, right? You should have a lightning protection system. But the codes don't require a lightning protection system. A lightning protection system for your home will cost $3,000 to $5,000, okay? And that sort of, not everybody wants one or needs one. Where I live, you know, the trees are going to get hit before I get hit, or the people living on the top of the hill are going to get hit before I get hit. Early days of looking at these things, I used to wonder, how come it's these great big homes on tops of mountains? Well, I knew by tops of mountains, but these were brand new homes because it's a brand new product. But they tended to be places with no trees, okay? And so out in the Midwest where, in the plains and stuff, there's not a lot of trees growing up, or new development doesn't have big trees and stuff. Older developments are not necessarily so bad, but in any case, there's a big fight going on, and it's going to be a huge fight over all of this stuff. The regulatory authorities kind of know what's going on now, that it has to be multiple point bonded, and part of it is people didn't think about the physics, okay, of a lightning strike. They didn't consider a lightning strike, and the companies took 3 years to get beyond high school electricity, okay? Until 6 months ago, they were still using the word resistance when they talked about the electricity. It's only in the last 3 months they've added the word impedance to their vocabulary, and that's because I've been telling them what impedance is for 3 years. So they finally learned about impedance. But you have no engineering capability within these firms, okay?
You know the OpenCourseware?
Well, I don't know. I could tell them. But would you like to have to take every course at MIT to find out what you're doing? That's why you need to go to somebody who, if you need to know electrical engineering, you ought to go to an electrical engineer. Auto mechanics don't cut it, okay? But anyway, so any questions? It's just sort of a story, a real life story of how a new product came to market, why it came to market, how it didn't have codes, no one thought about a particular failure mode. They found out about the failure mode, but at that point some people had too much invested interest in this, and so now they're fighting, and the regulatory authorities are fighting. Within 5 or 10 years it'll all get sorted out, and they probably will only be selling this type of stuff, okay? And this stuff is probably safe, and so we'll have an innovative product, and we will probably be selling less of this 10 years from now. But it takes time. It's going to take 20, 30 years for this to work its way through the system, okay? And so I'm sure there are 10,000 other stories like this. This just happens to be one that I've been involved in for the last 8 years or so. Okay, any questions? So we're sort of done. You're not done. You'll take a lot more. So how far are you now in the lectures? Oh, okay. So you got a whole another 5 weeks of, or not 5 weeks, but anyway. Yeah, actually you have about 3 weeks, or 4 weeks, 4 weeks of more lectures and a problem set. So if you have a question, or if you want to have another class as a recitation to go through some of the stuff you're getting in the lectures, or the video lectures, reasonably understandable, okay? There was a study done at Stanford. You can cut it off if you want. A study done at Stanford